sound. You can see the slides. This morning I showed some projections into the future of emissions of greenhouse gases. Did not really tell you where they came from, so that's what I'm going to do first, and then I'm going to talk about ways of reducing these emissions, and then next week I'm going to talk about the costs of doing so. So today we're just going to review the technical options. I showed this picture, which showed that there's a lot of things that influence our climate, but CO2 is one of the biggest ones. If you just take this is cumulative change in radiator forcing since pre-industrial times. These are just emissions, global emissions in recent times for all the greenhouse gases that we know of. In blue, we're looking at CO2. It's again the dominant thing. So if we understand CO2, we're beginning to get a reasonable grasp of the climate problem. And then there's methane, nitrous, and then sort of the industrial gases are very powerful on a molecule by molecule basis, but there are just not enough molecules of them around to have a very substantial effect. CO2 is broken down further. It's about 3/4 of emissions, right? In power and heat, manufacturing, transport, residential, sorry. And you see that, transport is big, 15%. Electricity generation as well as heat generation is twice as big, 30%. Manufacturing is about the same size as transport, it's about 14%. And then the stuff that is immediately or directly coming from your home is about 8%. So that is sort of a rough idea of what are the important culprits. So you should of course be very careful in saying, well, 30% of emissions comes out of power generation, but of course the power generators are not generating power because they like to, but they're generating power to sell it to you, right? So that is not counted here in the residential, but of course the final demand of these things does go to households. What sources of greenhouse gases are there? As I said, carbon dioxide is the most important, and the most important from there is the combustion of fossil fuels. Now it's important to realize that CO2 is not a nuisance in an engineering sense or in a chemical sense, but it's intrinsic to the process of generating, of getting energy out of fossil fuels. So if we're talking about a problem like acid rain, right, which comes from sulfur emissions from the burning of coal and oil, there if you ask a chemist or an engineer, what do you think about sulfur in the fuel? They say, well, this is actually a pain, right? Because carrying the sulfur around is not serving any useful purpose, and it's also an environmental externality. That is not true for CO2, because how do we get energy out of fossil fuels? Fossil fuels are carbohydrates. There's a lot of carbon atoms, there's a lot of hydrogen atoms. We heat it up, we add energy, we break the chemical bonds. And so far we've put in energy, but now the carbon atoms and the hydrogen atoms are going to reform or are going to form new chemical bonds with oxygen. So we create H2O and we create CO2. And it's in the new forming, or the forming of the new chemical bonds, that is where our energy comes from. So CO2 in a chemical sense, in a physical sense, is not a nuisance at all. That is where we get our energy from, right? And that's an important thing to keep in mind. If you want to get energy out of fossil fuels or out of any fuel, you have to create CO2. Not all fossil fuels are created equal. Per terajoule of energy that comes out, natural gas produces about 57 tons of CO2, petrol about 70, coal about 95, peat about 120. So we can actually already start thinking about how to reduce greenhouse gas emissions, how to reduce CO2 from fossil energy, and one way of doing so is to switch from coal to gas. These are CO2 emissions in black from the United States since 2001 to 2012. You can see that that's indeed falling. The reason is not because the US economy has contracted. It hasn't. The reason is not because of very stringent climate policy in the US, because there isn't any. The reason is very simple: shale. So what has happened is that, particularly in power generation, there's a new source of gas has come on stream called shale gas, which is much cheaper to burn than it is to burn coal. And what the power companies have essentially done, you see that here, that the black plus the red is roughly constant. There's a bit of oil in between. But essentially what has happened, and everything is measured in terajoules on this axis, essentially what has happened is that coal has come down, total is about constant, so gas has come up, and that is the sole reason why CO2 emissions, or the most important reason why CO2 emissions in the US have come down. Simple substitution of one source of electricity, or one source of one fuel for making electricity replaced with another one. We're looking at here are global emissions of carbon dioxide, given in black, from the early 70s to recently. And what we see is that over this period, emissions have roughly doubled. It's 1 in 1971, it's 2 in 2010, so that's a doubling of emissions. Everything is indexed so that 1971 is 1. We want to start understanding why did these emissions double. It is handy to make use of the so-called Kaya identity. The Kaya identity is named after Yuichi Kaya of Tokyo University, and he came up with this brilliant equation that says that emissions E equal the number of people P times per capita income Y over P times the energy intensity of the economy X over Y times the carbon intensity of the energy sector E over X. And you can't really argue with Kaya, because P cancels against P, Y against Y, X against X, so really the equation says that E equals E. It's an identity. The useful part of the Kaya identity is not the basic accounting, but that it allows you to decompose the trend in E, in emissions, and ask yourself, so what explains this? We've seen that carbon dioxide emissions doubled over this 40-year period. Population, you see here given in blue, increased by about 80% over a 40-year period. That's fairly rapid population growth, right, at a global scale. Per capita income also rose by about 80%. So people got almost twice as rich. There were almost twice as many people. If you add up those two trends, then CO2 should have not doubled but quadrupled. But it didn't. And the Kaya identity also tells you why it didn't. And nothing to do, or it had a lot to do with improvements in energy efficiency. They've come down by about 30% over the 40-year period, and a little bit of fuel switching has gone on as well, but not a whole lot. And you can also see that the initial downward trend in carbon intensity, essentially how much CO2 comes out of smokestacks per unit of energy generated, that trend had actually stalled, perhaps even reversed. The reason that it has reversed is because most energy growth nowadays is in India and China, and they're heavily reliant on coal, right? Whereas here we see a lot of energy use in Europe, Japan and North America, where there's been a steady switch from coal to gas. So that explains why it went down first, but went up later. It's important to keep this picture in mind. I'll come back to it a couple of times. So that was CO2 from the combustion of fossil fuels. There's other sources of CO2. Fossil fuels are old plant material, carbohydrates essentially, just like plants are carbohydrates. If you go through the process of land use change, that is, you chop down big trees and you replace them with small grass, then you also lose carbohydrates that are stored in the vegetation, and they're typically released to the atmosphere. Go ahead.
Is it carbohydrates or hydrocarbons?
It's the same thing.
Okay.
When they're sort of like fuel in your body, we tend to call them carbohydrates. When they're stuff in the ground, we tend to call them hydrocarbons. And the same thing, the same group of molecules. So that is a source of CO2 emissions. Cement production is another source of CO2 production. It's again intrinsic to the process. If you look at the chemical stuff, you take limestone, you stick it in a kiln, and you burn out the CO2 that is in there, or the carbon that is in there, and then you have cement. It's intrinsic to the chemical process going from limestone to cement that CO2 must come out. Similar things with methane. A big source of methane is meat and dairy. Ruminants produce a lot of methane. Cows, essentially, camels, that sort of animals. It's again intrinsic to the process. So essentially what a cow does is you stick grass in at one end, and then milk comes out the other, right? That's roughly how dairy production works. Now if you look at the composition, the chemical composition of milk, or for that matter steak, and compare it to the chemical composition of grass, you find that there's too much hydrogen in grass. So in the process of converting grass to the stuff that makes a cow, you need to get rid of hydrogen. Now, hydrogen is a dangerous gas. If you have hydrogen sort of floating around in an oxygen-rich environment, then it forms oxygen radicals, OHs, or hydrogen radicals, sorry, OHs, and that is pretty damaging if you have that floating around in your tummy. But there isn't a lot of oxygen in your stomach in the first place, so that is not a big concern. The second route for hydrogen is to form H2, and you have hydrogen gas. If you have a cow filled with hydrogen gas, you don't have a cow, you have a zeppelin. It goes up in the air, right? Because hydrogen gas is very, very light. Just the cow starts floating. It is not an evolutionary stable strategy for a cow. So what they did instead is they formed a symbiotic relationship with methogeneric bacteria in their tummies. And what these things do is that they sacrifice one useful carbon atom and take out 4 harmful hydrogen atoms and make CH4 methane, and then they burp it out. The methane comes out at the front of the cow, not at the back end of the cow. And that is just, they have to get rid of that extra hydrogen. Now, they formed this symbiotic relationship a long, long time ago. Kangaroos sort of have fill the same ecological role as cows. That is, they convert grass to meat. They solve this in a different way. They form acetate in their tummies. It's another way of getting rid of the excess hydrogen. And it also implies that if you want a carbon or a methane-free cow, you need to turn its metabolism into that of a kangaroo. Right? That's the sort of the genetic engineering task that is ahead of you if you really want to do that. And that immediately tells you how difficult that will be, right? Because the cows and the kangaroos separated from each other quite a while ago. Similar for paddy rice and waste. If you have organic material that is decomposing in an oxygen-rich environment, you create CO2 and H2O. If you have organic material, carbohydrates, that is decomposing in an oxygen-poor environment, it creates CH4. So what are those environments? Well, if you grow rice in a paddy, that is wet rice, you have a lot of organic material, still standing water, there's no oxygen, so it rots to CH4. If you have a landfill with a lot of food waste in, a lot of organic material, oxygen-poor environment, it rots to CH4, right? So those are two important sources of methane. With landfills, you can do something about it. You can put a cap on, capture the CH4, burn it, or sell it on. You can't really imagine doing something similar with all the millions of small paddy fields in Southeast Asia and South Asia and East Asia. Right? It's just completely impractical. The alternative, of course, would be to tell those people to stop eating rice, to start growing dry rice, which is much less efficient than paddy rice. So that is not an option. An alternative name for methane is natural gas, same chemical composition. If you're transporting chemical natural gas and your pipeline is not perfect, you will leak some. So that's another source of methane. Again, it's hard to get rid of this. Nitrous oxide is the same story. Essentially, nitrous oxide comes from fertilizing pasture land, fertilizing agricultural land. Farmers are risk averse, they oversupply nitrogen. Some of the excess nitrogen is converted in the soil to nitrous oxide and emitted from there. And the alternative to emitting nitrous oxide is to have much lower harvests. And then we have the industrial gases that come out of specialized industries. So that is where the stuff comes from. This morning I showed this picture with some of the colored lines showing alternative ways in which the future might unfold. We want to build a scenario like this. Then again, it is useful to go back to the Chi identity, which tells you that if you want to predict what are emissions in the year 2050, that's essentially what you want to do. You need to predict the number of people in that year. You need to predict how rich they will be, Y over P. You need to predict how much energy they use per pound value added. And you need to predict what sort of energy they will use. That's a pretty tall order, right? If you just focus on the P, how many people will there be in the year 2050? Some demographers are pretty gung-ho about their ability to do so. Complete nonsense. If you go to any sort of website about demography of population, you would find numbers. There's 7,853,744 people living at the moment. That is complete hogwash. In large parts of Africa, people don't have birth certificates. They don't have a proper population registry. Germany doesn't even have a proper, well, Germany does have a proper population registry, but you cannot access it for any other purpose than whatever it's signed up for. But you cannot in Germany, you don't know how many people there are legally in Germany apart from immediately after the census. You don't know how many people there are illegally in Germany. So we don't know how many people there are on the planet now, let alone that we can have some confidence in how many people there will be 50 years from now. Those things are fairly uncertain. To further illustrate this, the World Bank occasionally comes up with these population projections, and they have a middle scenario, and high scenario, and low scenario. And the last time round they did it, the high scenario and the low scenario differed about 1 billion people in the year 2100. And then last year they revised it, and the new revision has 4 billion additional people. So their uncertainty range only 5 years ago did not span their latest predictions. This is a fairly uncertain business. And then we can start about our ability as economists to predict future economic growth and energy use and so on and so forth. This is a very uncertain business. People have nonetheless tried. What you're looking at here is again the Chi identity, this population, per capita income, energy intensity, carbon intensity. The colored lines are alternative projections of the future. The black lines are observations in the last 40 years or so. Talked about population. The economic projections are fairly optimistic. So we've seen the economy grow in the past, and the assumption in all these models is that the process will continue indefinitely, or may even accelerate. Will definitely not slow down. So of course a lot of people in Africa and Asia hoping that this is true, right? But it's not guaranteed. This is energy intensity. We see sort of, with a bit of imagination, we see a negative trend in the past, but there's definitely been wobbles. And for some reason all our models assume that this trend will accelerate, that the past is not a good guide to the future, but actually energy intensity will, or energy efficiency will improve faster than it did over the last 40 years, and will continue to do so for a century. If you look at the carbon intensity of the energy sector, it's a rapid decline first, and then it sort of like veers up again. But for some reason the models all assume that the negative trend of the 1990s, of the 1980s will sort of continue indefinitely over the 21st century. We can talk at length about why these scenarios are as they are, but that's not really the subject of today. The short cut there is that this come out of these colored lines come out of the United Nations process where everybody's very optimistic and very nice to each other. So we're not going to tell, look, you guys, what you did is a lot of crap. So this is what is behind the colored lines you saw before. It's not entirely convincing. An important thing in sort of assessing what is the future of energy supply is the question, how much energy, and particularly how much fossil energy, is there in the first place? And this picture gives an answer to this. It's a complicated picture. So on this axis we have two types of gas, four types of liquids, oils, and 3 types of solids, coal. So that is relatively straightforward. On this axis we have what would happen to the atmospheric concentration of CO2 if all the stuff that is in the ground is burned in one go. So this essentially converts the reserves and resources of gas and oil and coal into changes in atmospheric concentrations. We can't do that, we can't burn it all in one go. And in one go I mean within 1 year. That's just not possible, but what if, right? And then there's color codings where reserves of oil and gas are that stuff that we know is in the ground and we know we can get it out of the ground with current technologies profitably at current prices. That is a reserve. And then there's all sorts of other stuff in the ground that we think in 10 years time we'll have the technology to get out of the ground profitably, or we think it's there but we haven't quite looked hard enough to make sure it is, and those are called resources, and they come in 3 gradations in this particular graph. Proved resources, probable and possible, and the lighter the color the less likely it is that they will ever be used, right? So that is what the graph shows. But what does the graph really show? Well, if we take natural gas, the reserves of natural gas, and we add to it our reserves of crude oil, then we get something like 100 ppm. We don't really change the climate a lot with that. That would add half a degree, maybe less. So that cannot be the problem. There's simply not enough conventional oil and gas to substantially change the climate. If you want substantial climate change, you need to add 200, 300 ppms. And that means that you need to find an alternative source of fossil energy over the conventional oil and the conventional gas. That is what will drive the climate problem in the future, not the gas that is in Russia and Qatar, not the oil that is in Saudi Arabia and Kuwait. But once we have run out of these things, what will replace that? Will it be American shale? Will it be Venezuelan extra heavy oil? Will we go back massively to Australian, Chinese and Indian coal? Those are the questions that drive the climate problem, not what will happen to the conventional oil and gas. There's simply not enough of the stuff around to cause a substantial climate problem. This also gets you into political discussions, because if you sort of listen to the rhetoric about climate policy, and it's the evil Russians and the evil Saudis and the evil Kuwaitis and the evil Qataris that are causing the problem, or the Shells and the British Petroleums and the ExxonMobils. They're all in the conventional oil and gases. They are not the source of the problem. The problem is coal, the unconventional oil and gas. That's where the problem lies. The chi identity that I've now shown twice, but for some reason notation has changed, also tells us how to abate emissions. And so if this thing is true, then what we can do, and there's no argument there, that what we can do is take the log at both sides of the equation, then it's still true, and then take the first partial derivative to time at both sides of the equations. And then we get this expression here. This may be an expression that's slightly unconventional or unusual to you. but this is just proportional growth rate, right? Because if you take d ln x dt, partial derivative of ln x to x is 1 over x, and we have to use the chain rule, so we have dx dt, so we have the proportional change in x over x itself, so that's a growth rate. So essentially what this says, that the growth rate in emissions is the growth rate in population plus the growth rate in per capita income plus the growth rate in energy intensity plus the growth rate in carbon intensity. That just follows immediately from the chi identity. So that implies that if we want to reduce emissions, we can cut the number of people. Active policy in the Sudan, an active policy in Zimbabwe. But also the Chinese often claim at international climate gatherings that their one-child policy is their biggest contribution to climate policy, and we should all be very grateful to them. If you stand for election or re-election in the UK, saying that we're going to cut the number of English people, at least, you would not get re-elected. If you want to throw out foreigners, it's a different story, right? But it's a way of reducing emissions, and not necessarily one that gets you elected. Similarly, reducing economic growth is an option to reduce emissions. The former Soviet Union has been terribly successful in this. When the Soviet Union collapsed and the wall came down, some of these economies shrank by 30, 40, 50%, and they took emissions with them by roughly the same amount. Similarly, in Europe at the moment, the euro crisis has substantially reduced emissions as well. But again, it's not something that will win you elections. There are some people out there, also in England, who sort of like say the climate problem is so important that we should reduce economic growth, we should go to an economic shrink scenario even. Kevin Anderson of Manchester University, not United, is one example. We have to cut emissions by 10% per year. The only way to do it is to shrink the economy with 7% per year. But yeah, Kevin has never stood for election. And for some strange reason, not even the Green Party has taken up his policy recommendations. So if you're sort of constrained by elections, right, you cannot touch population growth too much, you cannot touch economic growth too much, then the only way to cut emissions is to improve energy efficiency and to improve carbon efficiency. And to do it in such a way that it is stronger than population growth and economic growth combined. Right? That's the only way to reduce emissions. These things are positive. If you want this one negative, this has to go very negative. Right? Going back to the graph I showed before, that is not necessarily easy. Because energy efficiency is improving in and of itself. And this has nothing to do with climate policy. There was no climate policy for most of this period. This has everything to do with the fact that energy is costly. If you're a manufacturer and you can offer a product with the same characteristics as the product of your competitor, but one that is more energy efficient, then it is cheaper for your clients to run it, and therefore they will buy it over the product of your competitor. And this is a pretty strong process. People like Roger Fouquet, Bill Nordhaus have extrapolated or have reconstructed energy efficiency improvements for hundreds, and in Nordhaus' case for thousands of years, and they find that this has been going on at least since Babylonian times. And energy efficiency has constantly improved because energy is a cost. Now, some people get a little bit confused there. George W. Bush is a prime example of somebody who was a bit confused. One of the key parts of the Bush climate policy was to improve energy efficiency by 10% per decade. That was an announcement he made, and he seemed very pleased with himself for making that announcement. He completely forgot that when he made that announcement, the previous 3 decades energy efficiency had improved by 18% per decade already. And he was not suggesting to push it from 18 to 28%. No, he was saying we're going to do 10% in the future. And he's not the only one. Also politicians who we think are smarter make basic mistakes like this. So what can you do to save energy? As I said, a lot of it comes basically through technological change. There's also behavioral change. If we consider a single product, then we see that over time energy efficiency always improves. Did not put in that particular slide. That does not mean that the energy efficiency of the sector also improves. If we look at fuel efficiency fleet average in the US between 1980 and the year 2010, it was basically stationary. There was no improvement in fuel efficiency in the average fleet for 20-30 years. Which is actually, if you look at it closely, is quite amazing, because at the same time the size of the cars doubled, if not tripled, and the weight of the car similar. So the fuel efficiency of the car stayed the same, but the size of the car grew, and therefore the engine had to pull a lot more weight. And if you then do it, you still get the same miles per gallon, then obviously the energy efficiency of the engine itself has improved drastically. But because energy prices were so low for most of that period, consumers rather wanted a bigger and more comfortable and presumably safer car than a more fuel efficient one, right? So these technological improvements, though potentially they reduce energy use, they do not necessarily. Behavioral change can also save energy. It's hard to affect this from the perspective of central government. Some of it is just habituation. For instance, if you want to make a cup of tea, you boil a kettle. A lot of people put way too much water in the kettle, boil all this stuff, and it's not used. You just let it cool down again. It's a sheer waste of energy. Engineers reckon that about 30% of the energy that we use serves no useful purpose. But going back to the example of boiling your kettle, how do you change this? Some of you may live in a house with an energy Nazi, some of you may be energy Nazis, right? I tell my kids, yeah, you don't need to boil all that water. I'm their dad, I can sort of say that. But if you sort of like live in a house with 4 or 5 other students and one of them does this all the time, do you really want to go into the conflict all the time? You should not, every day, every morning, every evening, you should not boil so much water. There's a big social price to pay for enforcing this, and obviously David Cameron or Ed Davey does not come look at our houses and say, how much water do you boil every morning, right? From a central government perspective, this is completely beyond bounds, and the only thing we can do is sort of gently persuade people to stop being so silly. There's deeper problems as well, and they are economists would call them principal agent problems. If you walk around the university campus at 5 in the afternoon, you would find that there's a lot of lights on. You would find that people leave on the beamer or their computer in lecturals, even though there's nobody there anymore. That's a waste of energy and a waste of money, right? But what happens if I am a good boy and I turn off the computer and I turn off the lights when I leave a lecture hall? The energy bill of the university goes down. That is money that goes to Michael Farthing. That is not money that goes to me. That doesn't help me at all. It disappears in some big university pot. It's a principal agent problem. I am the agent. I control the resource. I control the lighting in a lecture theatre. Michael Farthing is the principal. He pays the bills. And our interests are not aligned, right? Those things are hard to solve. The way to solve it is to hire an administrator who goes around and turns up the lights. That's costly. Or that every lecturer in this university has their own personal electricity bill. And before we enter into a lecture hall, we have to type in a code. It's me now who's controlling the lighting. And both sort of like are costly and create problems of social control and so on and so forth that perhaps we don't want to go into. Third way of reducing energy use is, of course, to use less energy. To say to people, yeah, just turn down the thermostat and put on a sweater. Or take your holiday in Dorset rather than in Thailand this year. And those things are also not necessarily popular ways of reducing emissions, right? Those things are just, it's hard to convince people. Small minority will sort of say, yeah, I think climate change is an important enough problem that I would go to Dorset rather than to Thailand. And we'll just pretend that the weather is just as nice and the landscape just as beautiful. But most people say, I'd rather go to Thailand or some similar place, right? So then the second option in the Kaya identity that is sort of viable is to switch to alternative sources of energy. There's no physical problem here. If we just add up the amount of energy that is in wind and in water and in solar, then we can supply the world's energy needs 10 times over. There's also no technical problem. We know how to convert solar into electricity. We know how to convert waves into electricity. In fact, there's many alternative technologies for doing so. So the resource is big enough, and we know how to convert this sort of energy into something that we could use. The problems are economic, social, political. Nuclear and hydro are relatively cheap options for, and carbon-free options for making electricity at least. But large dams require that we flood villages and have to move people. We flood nature reserves and have to move animals and kill plants. So it's not necessarily popular. A lot of people are terribly scared of nuclear power, and there's a lot of resistance against it. So even though these are sort of technically and economically feasible options, politically and socially they're just difficult. Wind power is expensive. So roughly speaking, if you want to generate electricity, coal will get you there for 4 pence per kilowatt hour, gas would get you there for 6 pence per kilowatt hour, wind is still in the range of 8 cents per kilowatt hour. So it's simply twice as expensive as the cheapest option. And there's more and more resistance against the visual intrusion of all these wind turbines. There's issues with bat populations, bats being killed, some birds being killed. There's issues with safety. We've now so many wind turbines that Some must be faulty, right, regardless of your quality standards in manufacturing, and occasionally these things fall down. Fortunately, they've never fallen on somebody's head, right, but that's just a matter of time. So wind is an issue there. Solar is more expensive still than wind, still in the range of 10 pence per kilowatt hour or up. Some of these markets it actually works fairly well. There's problems with both wind and solar. Wind is unpredictable. You never quite know when there's enough wind to meet all your electricity needs. So engineers disagree and argue that wind can only supply 10, perhaps 20, perhaps 30% of your total electricity supply, and after that it simply is too unreliable to run a country on. Solar has the same issue, that you have a lot of solar when the sun shines, but unless you go to concentrated solar power, there's no momentum there. So as soon as there's a cloud before the sun, your electricity supply goes down. It's not necessarily what you want, definitely when it gets dark. Solar power is not necessarily your best source of electricity. People are working on the storage problem of storing massive amounts of electricity for short periods of time to get us through the night, to get us through a lull in wind. But it's not quite solved, and it's fairly expensive still. And there's other issues with wind and solar, namely that the best solar resources are far away from where we are. So the Sahara would be sort of an obvious place to put big solar farms. It's a problem. I mean, we don't really like the Saudis, and they don't really like us. We're getting, at the moment, getting a lot of oil from them, and neither party is terribly comfortable with this relationship. We could, of course, instead put solar panels in Morocco or in Egypt or in Algeria and see how that will improve our relationships with these countries, right? They're not necessarily our friends either. And of course, as soon as you start transporting electricity, A, you lose a lot of electricity on the way, and B, it's terribly expensive. Now, wind and solar and nuclear and hydro bring electricity. And electricity is great if you want to charge your iPod or your iPad or whatever, or want to run or turn on the lights. It's less handy if you want to drive a car around. Electric cars are not quite there yet, not quite ready for prime time. The prime candidate for delivering transport fuels that would be sustainable or would be CO2 poor or CO2 free is biomass. There's big issues there as well. At the moment it's terribly expensive. I mean, if you think that solar is expensive, then wait till you see biomass. The reason that it's so expensive is twofold. On the one hand, you can say fossil fuels are biomass that have been neatly compacted over a few million years by gravity and geological processes and that sort of stuff until the energy density is quite high. Essentially what you do if you say you want to convert a field of corn to fuel is you need to compact this, but now you need to do it yourself. You need to transport it, you need to remove the water, you need to process it, and so on and so forth. It is simply, you need to do a lot of things that if instead you go to coal or oil, Mother Nature has done for you already, right? So it simply can't compete on that basis. The other way of looking at biomass is to say, well, over the last 10,000 years or so, we've actually done a great job of optimizing plants for food. And if you look at our modern crops and compare them to their wild ancestors, they're completely different and they're much more useful to us. We had never bothered to do this for energy crops, which is why we're so far behind. But also because we've learned so much over the last 10,000 years and definitely over the last few decades about breeding, selective breeding, about geoengineering and all that, about genetically gene engineering, I should say, we can actually expect a lot of progress there. And we've seen successful experiments in the lab where people manipulated algae, put them in a vat, and then 2 days later they had a film of diesel floating on top of the vat. We're getting there, but we're not quite there yet. I mean, there's been a number of these technologies that have been developed that work very well in the lab, but none has made it to the field yet. But that is just a matter of time. But at the moment, none of these alternatives is particularly attractive. Technological progress in wind is basically stalled. Technological progress in biofuels is very, very rapid. Technological progress in solar is also very rapid. So give it a few decades, and these will be mature technologies that will compete with whatever fossil fuels there are. Not at the moment. There's other options for reducing greenhouse gases. We can grow trees, suck out carbon. We can capture the CO2 before it goes into the air, stick it in the ground somewhere. Or we can just say, well, if you can change the climate one way through CO2, we can also change it, the climate the other way by putting dust in the atmosphere or mirrors in space. You can read about that in the book, and I'll see you guys next week. The first 2 computer exercises are due Sunday at midnight, right?
Not this Sunday, next
Sunday
Sunday.
at midnight. Yes. Okay, see you guys.